Hello, everyone. The following is the first in a series of lectures covering chapter 36. This chapter talks about the use of lenses and mirrors to create images that are a lot easier to see than the object you are trying to look at. Last chapter, we learned about reflection and refraction. And we may ask ourselves what that is good for. The answer to that is mirrors and lenses. So, because my eyes are stuck to my face, it's hard to shave without a bathroom mirror around, since I can't really see where my razor is moving unless I can see my own reflection. So, taking advantage of the low reflection that lets me see my own face helps me shave. And even when you're driving, right, you have the rear view mirrors that keep you from turning your head every time you want to see behind you, right? They reflect light behind you towards you, so you can see the cars creeping up on you. And the effect that refraction has of bending light away or towards a normal can basically magnify or minify images and change the points at which light gets focused. In other words, lenses are like prisms where they take advantage of refraction to bend light. And this is just a fancy way of saying that lenses help correct your own vision. I wouldn't be able to see more than a few inches past my face if it wasn't for the correcting glasses that I wear. So, simple tools like mirrors and glasses, or even more complex ones like telescopes and cameras, take advantage of reflection and refraction to see things more clearly. For talking about the physical geometry of objects and how their light gets reflected or refracted, we're going to be using a fairly simple setup. So imagine that we have a screen that always shows us the cross section of a mirror, and the mirror or perhaps a lens is usually placed in the center of the screen, and we'll have the object that has light that gets reflected or refracted by the lens or mirror in the middle. That object's usually going to be placed on the left side. So for a flat mirror here, we have our object, and a few important things about the geometry in general is that wherever you place the object, we're always going to talk about the object distance, which is just the distance from the object to the mirror or the lens. So in this case, you put an object in front of a mirror, and some of the light coming off the object, because it's suppose that you're in an illuminated room, so some light from a lamp somewhere hits the object, and that bounces off the object into the mirror. By law of reflection, those rays are going to get reflected back, and somebody standing by the mirror can see the object's reflection. So if you look at this example here, where something is bouncing off the mirror, the rays coming off the object are fairly close together. They fan out as they hit the mirror, and as they get reflected outwards towards the lower left, they diverge even more. So they come out, converge, and basically keep going farther and farther away from each other. It appears then that the reflected rays are coming from a direction behind the mirror. So you can actually draw some dashed lines to where the reflected rays appear to emerge from, and you'll see that they would theoretically intersect behind the mirror. The reflection of an object is referred to as the image. And wherever the reflected rays appear to intersect, even though they're not physically intersecting. In this case, they appear to be intersecting behind the mirror, but there's no actual physical space behind the mirror. The reflected rays are created at the interface, right at the surface of the mirror. It's just that they appear to come behind it due to the fact that they're aligned in such a way that their intersection would be behind the mirror. Where those rays appear to intersect is where the reflection is, where the image is formed. So, in terms of the geometry, we can talk about the distance between the mirror and the image. That distance is called Q. Again, by looking at the reflected rays, you can trace them back to the point where they would intersect, and that point where they intersect is the location of the image. And in some cases, the rays are not physically intersecting, but you can still locate the image by tracing them back. So whether the light rays, the reflected light rays actually diverge or appear to diverge, that's where the image is. If the light rays are actually diverging in front of the mirror, so they're actually physically coming out of a point, then that's what's called a real image. If the reflected light rays do not pass through the image point, they only appear to diverge from the point behind the mirror, that's called a virtual image. In this example here, where we have a flat mirror, the image is virtual because it appears behind the mirror. But again, there's no actual light rays that exist behind the mirror. It's just that the light rays appears to be diverging from where the image is located. In the case of a flat mirror, the image is always virtual. So, right, any mirror you've looked at in any living room or bathroom, you always see yourself behind the mirror. You always see a virtual image. Now, this slide here takes notes directly from the textbook, and what it's just talking about is some more geometry where you draw this rays of light coming from an object placed in front of a flat mirror, and with some geometry arguments and the law of reflection, you can determine that for a flat mirror, the magnitude of the object distance is equal to that of the image distance. In other words, they're equal distance from the mirror, which just seems pretty obvious, right? I'm looking at my office mirror right now, and I'm standing about 3 meters from it. My reflection seems to appear that it's standing 3 meters behind the mirror. If I walk towards it, my reflection also walks towards it. So it's just that now we can use ray optics. We can look at this cross section of a mirror where the object is, and we can use ray diagrams to figure out where its reflection is going to be without even having to glance so much at an actual mirror. Now, not for flat mirrors, but I'm sure you might have tried using like a makeup mirror or like one of those shaving kit mirrors, or even like the rear view mirror. Any mirror that's not flat, you'll note that the images that they reflect aren't the same size as what they're reflecting. So in your rear view mirror, the cars are tiny, but the actual cars on the road behind you are much, much bigger. So mirrors can obviously then make something look bigger or smaller. Like makeup mirrors can make your face look bigger on them so that it's easier to apply foundation. Now, we would then are able to talk about how a mirror warps an image, how a reflection can be made bigger or smaller depending on the type of mirror. For simplicity, though, right? If you think about the kind of like the makeup mirror example, your whole face kind of gets stretched out in all directions. But since we're only looking at a cross section of a mirror in these ray diagrams, we're only going to talk about how the object gets magnified in the vertical sense. So, because In these ray diagrams, the cross-section of the mirror spans vertically, so we're only going to talk about the lateral magnification of the object. But in the real world, where mirrors are 3D surfaces, right, an object is magnified both vertically and horizontally. So the lateral magnification, written as M, is just the ratio of the image height to the object height, which, if the ratio is bigger than 1, the image is bigger than the actual object, and if it's less than 1, it's smaller. So for your rear view mirror, rear view mirrors have a magnification of usually less than 1, because to make all the cars look smaller than they actually are. For a flat mirror, there's no magnification, right? Look at your own reflection in the bathroom. Your reflection's the same size. And that's true for anything you put in front of a flat mirror. So the term's magnification, but because it's just a ratio of the sizes of the image and the object, it can be bigger or less than 1, like I said. So mirrors, reflected images, can be made bigger or smaller depending on the type of mirror and where the object is positioned. So here we have a makeup mirror that makes your face look bigger, and then a corner mirror that makes this whole church looks like it fits inside the frisbee. Also, you may note that your reflection is the other hand that is your dominant. What I mean is that I'm left-handed, but if I raise my left hand, my reflection seems to raise its right hand. But when I raise my left hand, my reflection's right hand still on the left side of the mirror. So it's not actually that like the left and right direction is flipped on the mirror. There's no horizontal flipping that the mirror does. Nothing is flipped on a y-axis. What the mirrors actually do is they reflect the front and back of the objects. So when I put my hand up to a mirror, the front of my hand is where the back of my hand is, and vice versa. So this swapping of back to front makes my left hand get reflected as a right hand, but the mirror doesn't actually reflect left and right. It's just that the front-back reversal causes things to not point the other way, but simply change handedness. The textbook shows a good example of this, where like if you lay down on the floor, right, your body's now parallel to the floor. If you shake your head, your head shakes, not your feet. So everything on the left side still on the left side on the reflection. It's just that the front back change makes everything look flipped. So quick quiz here. You're standing 2 meters away from a mirror, and there's water spots on the surface. Is it true or is it false that it's possible for you to see the water spots and the image both in focus at the same time? So for your eyes to focus, right, they have to adjust themselves so that the light from an object concentrates directly onto your retina. So when objects are at different distances, your eyes can't concentrate on both because there's only there's a particular adjustment to your cornea, to the lenses inside your own eyes that brings an object into focus. So while you're focusing on one object, you can't focus on another. If you're standing 2 meters away from the mirror, your reflection is 2 meters behind it. In other words, there's a total distance of 4 meters behind you and your reflection. So your eyes will need to focus 4 meters away from you to get a clear view of your reflection. The water spots on the surface are 2 meters away from you. So you can't focus on the water spots and your reflection at the same time, since they are different distances, and your eyes will have to make a different adjustment to see them respectively. So it's false. Anyhow, next time we'll talk about spherical mirrors, so I hope you join me then.